Alright, so we're going to talk about geometric probability today, and this is kind of important because we have a whole unit on probability at the end, and you've probably had some experience with probability already as we wrap up chapter 11 here. So it really boils down to what we want divided by the total. And what we want is phrased in the question, like flipping a coin if we want heads. So what we want is heads, and that happens one time. And the total is heads or tails, so that's 2, so it's 1 over 2. So the probability of flipping heads on a fair coin is 1 over 2. What we want, the 1 heads, and the total, the 2 choices, heads and tails. So that is the basic idea of beginning probability. It gets a little more complicated later on. But so in geometric probability, the things that we're looking at have a geometric aspect to it. So one is length. Okay, so you can read this. Let segment AB be a segment that contains the segment CD. So CD is part of AB. If a point on AB is chosen at random, then the probability that it is on CD is what? So the probability that a point chosen at random is on CD is going to be the length of CD divided by the length of the total. So let's color code that up a little bit here. So CD, the length of segment CD, compared to the length of the whole thing. All right, and that's pretty much that. And we could do the same thing here. So the same thing applies to area. So the area of the whole space that we're looking at looks like a trapezoid, but I don't know if they didn't really give us enough information to say that for sure. So the J is looks like a trapezoidal region, and it contains region M. If point K in J is chosen at random, then the probability that that random point is in M is the area of M divided by the area of the entire area that we're looking at. So in each of those cases, it's what we want divided by the total. So want divided by, whoa, that'll cut down on the shadow or not, but want over total. So that's what we're looking at. Okay, so let's look at an example here. So each circular hole on a target has a radius of 0.5 feet, so that would be 6 inches. If a beanbag is equally likely to land on any point on the target, find the probability that the beanbag goes through one of the holes, assuming that it hits any part of the hole that goes through the hole. Or maybe not. The center of the bag is within the hole. You don't have to worry about those details. So basically what we want is the beanbag to go through one of the holes. Now, we all know, any of us who have played cornhole before, or I don't know if you have a different name for it, but you know that you don't, well, maybe you do if you're really good, hit the board every time. But every once in a while, maybe we miss the board. And that doesn't account for also sliding and stuff like that. But so what we want is the beanbag to go through one of those circles, and the whole thing is the board, assuming that it's going to hit the board. For when it hits the board, what's the probability it goes through a circle? Now, we would hope that our aim doesn't make it random, that we actually are influencing where the beanbag goes. But anyway, so let's take a look. So we want the area of the hole. So first of all, let's find the area of one of them. So the area of a circle is pi r squared. Okay, so that's going to be 1/4. So that's going to be pi over 4 is the area. Feet squared is the area of one of those circles. We don't need the units because they're going to cancel out. And there are 4 of those circles. Each circle has an area of pi over 4 feet squared. So when we multiply that out, we're just left with pi. Okay, and now when we look at the total area is this rectangle. Doesn't really say that in here, but let's throw some right angles on there, make it a rectangle. So that's just going to be 3 times 4. So that's going to be 12. All right, and like I was saying, this would be feet squared and this would be feet squared, and we can cancel those out. Probabilities don't have units on them. It's just percentage or fraction, which, as a matter of fact, we can kind of think about this as a fraction. So pi is a little bit more than 3. So if we did 3 over 12, that reduces to 1 over 4, which would be about 25. But we know that that pi is more than 3, so we know that this is going to be more than 25%, approximately. Okay. Now, this is a little bit strange because we're gonna kind of force it into a geometric situation. So you ride a bus to work. The bus comes every 15 minutes, and the ride to work is 31 minutes. You arrive at the bus stop at 8:24 a.m. What is the probability that you'll be to work by 9 o'clock? Okay, so if we take, let's see, in class maybe I would see if anybody had any ideas here where we should start. So we want to be there by 9, and the bus ride is 31 minutes, so that's where we want to start. So if we take 9 o'clock and we subtract 31 minutes from that, now you got to be careful here because 9 o'clock, that's 60 minutes. So you really want to think about that. So really maybe what we should do with that is rewrite that as 8 and 60. 8:60 is 9 o'clock, 8 hours and 60 minutes. So we kind of broke one of those hours up into 31 minutes so that we could subtract that. So that would be 8:29. So 8:29 is important. Okay, we get to the bus stop at 8:24. So if we want to be to work by 9 o'clock, we need to be on that bus between 8:24 and 8:29. So you can think of that as a line segment. Time, linear. There's some argument that that's a much higher level discussion about time being linear than we're going to do in honors geometry. But so we're looking for this 5-minute window between 8:24 and 8:29. That's what we're hoping for because that will get us to work by 9 o'clock. Now, the buses come every 15 minutes. So that looks more like this. So if we take that ratio and we put 5 over 15, 5 over 15, that's going to be 1/3. So we got about a 33% chance. Now, I would guess that the buses, there's a schedule, and it doesn't just randomly come unless there's things that come up. But so probably knowing the bus schedule with our phones, we can look those things up nowadays. In the past, it was a little bit harder. Sometimes they were on the bus stop, sometimes not. Okay, so let's move on. So we kind of created line segments to represent the time, and that's kind of what makes that geometric probability there. Okay, the shaded area in the diagram of a yard shows the area that you can see from your window. Okay, if a child is equally likely to play in any part of the yard, what is the probability that you will be able to see him from the window? So, I guess my thought would be that if you're worried about seeing the kid in the yard, maybe you should go out in the yard, or I don't know. This seems to be not a good way to watch your kid. Well, I can see them if they're out here, but that's just my opinion. I guess it depends how old the kid is. I guess the older the kid is, the less, well, I guess that's not, I was going to say less supervision they need, but that's probably not always true either. So, okay. So I've been just kind of using purple for what we want, and purple for the whole thing, the total, and green for what we want in these examples, just to have some consistency. So what we want is the green thing here. Now, if you look down here and you add these together, if you add this to this, that's 32. 32 and plus 32 is 64. So we know that these sides are all equal. I guess we don't know that for sure, but again, really we should have some right angles on here probably to show that it's a square. So the yard's a square, and so we want to focus on this. This is a trapezoid. So the area of a trapezoid is the average of the bases, which would be 5 plus 64 times the height, which would be 64. So that's our formula for the area of a trapezoid. That's kind of important, especially if you are going to make it to calculus one day. We use trapezoids in calculus. So the area of a trapezoid, average of the bases times the height. Now the square, that's just going to be 64 squared, or 64 times 64. So those are going to cancel out pretty nicely. Now, this is odd, so if I add those together, that's going to be 60, and then, oops, I was supposed to use green for that. Now, over here, this is a complex fraction. Remember, we have a fraction with fractions in it. We call that a complex fraction. And so an easy way to deal with that is just to multiply by 1. So we're going to multiply by 1 right here. So that is going to cancel this out. 2 times 1/2 is 1. And now I can multiply this by 2. So that's going to be 128. And we can see that's a little bit more than 50%. So probably, depending on the kid, that might not be a good percentage. It's not very much. It's half the time the kid's wandering around. Okay, now we're going to do some review. Alright, so the rest of this is review. So what you should do is you should fast forward. Well, you should look at the questions, and if you look at this and you're 100%, you're like, I know how to do this. Now this one's actually a bit tricky. Now it says use a hint right here, 4 triangles and a rectangle for the area. So you can't just use a regular area formula, you got to kind of do some work in there. So this one's a bit tricky, so you might want to do this one. But as you look through these, we've done this one a bunch of times. So you may want to look for questions that you're like, yeah, I don't know how to do that, or I'm not sure about this. You might want to do this one, and then fast forward these notes until you get to that, and then check it. And so you need to be mature enough and have discipline enough to do the questions that you need help on, that you need to see done. Okay, so I'm going to get started here. So this one is point slope form. So we take the opposite of x, and we take the opposite of y, and then we apply the slope right here. So 1, -1 is right here, and the slope is up 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4. It's a positive 3, 4, so that's why I know 1, 2, 3, 1, 2, 3, 4. So since I went down, I go to the left. 1, 2, 3, 1, 2, 3, 4. Okay, so that is right here. And moving on to the second line, that's in slope-intercept form. So that tells us we have when x equals 0, y equals 3. So that's 0, 3 is up here. And the slope of that one is -4, which happens to put us right here. 1, 2, 3, 4 to the right 1, or 1, 2, 3, 4 to the left 1. Because that line needs to go down, because it has a negative slope. Okay, and I aim for the furthest 2 points. That should keep my line where it needs to be, hopefully. Now remember, one thing when you're graphing these in our class is these lines should intersect perfectly. So that's off a little bit, but I know that that's where it's supposed to be. Okay, this next one is in standard form, and in standard form we normally, and you'd write these names down if you need to. This one is standard. The red one was slope-intercept. And the first one was point slope. Be using lines, graphing lines in your next couple of math classes. So if we let x equal 0, then we divide both sides by 4, y would equal 3. And if we let y be 0 and divide both sides by -3, we get -4. So 0, 3 is right there, and -4, 0 is right here. So I guess we don't know what side that is on yet, so up 3 over 4. And how do I know that? Because I can see it right here, because these are the two intercepts. So I can see that goes up 3 to the right 4, so that's 3/4. So follow that same pattern across. Now on our tests in class, a lot of times we would have you'd have to graph more than one thing, and so sometimes you would want to erase part of this so that you could fit another shape on the graph, but we're not really doing that in this situation. So this is also point slope form. These two kind of, so the point is the opposite of x and the opposite of y. So -3, -4, -3, -4. So that's right here. And the slope is -4. And so I don't really need all the points because I can see that by connecting these two sides I'm going to get this shape right here. And again, like I said, sometimes we have other graphs on there, so you'll notice that on the ones we assign the test from last year. And so even we could erase part of these lines if we need to. Don't erase it all the way down though, because it says graph the lines, so they should have arrowheads on them. Okay, so hopefully you notice that both the green and the purple both had slopes of 3/4, and these both, the red and the blue, had slopes of -4. So that is a parallelogram. Opposite sides parallel. Okay, now it says find the area and the perimeter. So first of all, perimeter is going to be units, and area is going to be units squared. So we could do that right away. Now I'm going to define the perimeter first. So this is actually pretty nice because this is 3 and 4, so that's a 3, 4, 5. So that's 5, which tells me this is also going to be 5 down here. So 5 plus 5 is 10. So we have 10 so far. Now the other ones are right triangles. So it's a little bit tricky to see, that's kind of small, but that's 1 and this is 4. Okay, 1, 2, 3, 4. So if we use the Pythagorean theorem, we say 1 squared plus 4 squared equals c squared. That would be 1 plus 16, which is 17. And we take the square root of both sides. And that's actually pretty nice because that doesn't reduce or simplify. So that's going to be radical 17. And hopefully everybody sees over here, this is also 1 and 4. So that's going to be radical 17. So we're going to have 2 radical 17s. One on each side. So there's our perimeter. Now we need to find the area. Now the area of a parallelogram is the base times the height. But we don't have the height. The height needs to be the perpendicular distance between there. We don't really have that, and that would be pretty tricky to find. So what we can do instead, the directions say use 4 triangles and a rectangle. So if we do this, and some students have a little bit of a hard time figuring out where do we draw the triangles and what do we have there. But so hopefully you can see the rectangle in here. That is 3. 3 times 1. So the area, that's 3. Now we could do these triangles separately and then multiply that by 2, but I hope you see that this is 1 and 4 and this is 1 and 4. So if you think about it, I'm going to just put those together over here. So, except I do that too big. Alright, so if we do that and we put those two triangles next to each other that are 1 by 4, we get a rectangle that's 1 by 4. So those two skinny triangles add up to an area of 4. So we've got 3 in the middle, and then we have the two smaller triangles add up to an area of 4. And then if we put these two together, you could do that up here also. So that's 3 and 4, like this. And we could go 3 and 4 right here also. That's putting these two triangles together. So that's going to be 3 times 4. That's going to be 12. So 7 plus 12 is 19. So we're not using a formula. Normally we use a formula if it's straightforward, but it's not. So, all right, I'm going to just move quickly. So again, you should be fast forwarding. Like if you totally know how to do this, you've gotten it right every time. You don't need to watch it again. It's okay. Just move to the next one that you need to do. Fast forward. Although pause this and do it first, then fast forward till you get there, unless you need to see how it's done. So here we probably should sketch a triangle. As soon as I see the word hypotenuse, as soon as we see the word hypotenuse, we should realize that is a right triangle. So we have the hypotenuse there. Shorter leg, shorter leg. So they're both going to compare the shorter leg. That's going to be x. Hypotenuse is 2 less than triple. Longer leg is 2 more than twice the shorter. 2 more than twice the shorter. So we're going to have x squared plus 2x plus 2 squared equals 3x minus 2 squared. Okay. So you could draw a box and use the area model. So this is 2x plus 2, and this is 2x plus 2. So that's kind of small, but that's 4x squared, 4x, 4x, and 4. So we've got x squared plus 4x squared plus 8x plus 4. Now really, we ought to be able to handle multiplying this out. You just square the first thing, and then you multiply those together and double it, so it's going to be minus 12x, and then you square the last thing. Okay? So if we subtract 4 from both sides, those are going to cancel out. I like to keep my first term positive. So I have 5x squared here. I'm going to subtract that over there. That's going to be 4x squared. It's a good idea to actually write it out, but math teachers skip that a lot. And then subtract 8x from both sides. That's going to be minus 20x. So that has a GCF, greatest common factor. I know I'm going a little bit fast here, but just pause it if you need to. Pause for each step, because some people just want to zip through this. So that's going to be 0 and 5 for our possible answers. But if we plug 0 in here or here, that's going to be a problem. So the answer is 5. Okay. What are the ratios of the perimeters and the areas of similar polygons that have a scale factor of 7 to 9? Well, the perimeter has the same scale factor as the sides. So that's going to be 7 to 9. The area, however, remember area is measured in square units. So that would be 7 squared over 9 squared, or 49 over 81. And it looks like those might simplify, but they don't. They're both perfect squares. That's why they look like something's happening, but not happening. Okay, so going through this, we want to say, first of all, the first thing you should check is it a triangle? And you do that by adding the two smaller sides together and comparing it to the third. The two smaller sides have to be greater than the third side. Here they are not, so there's no triangle. So that's probably our favorite because we don't have very much work to do there. Okay, here, the square root of 11. Well, that's in between the square root of 9 and 16, which is 3 and 4. So that's in between 3 and 4. So that's going to be 3 point something. This is also in between 3 and 4. So that's going to be 3 point something. And this is between 4 and 5. So that's going to be 4 point something. So the two smaller sides are bigger than the third side. So now we're going to take the square. So we're going to take 11 squared plus 13 squared, the square root of 13 squared, sorry, and compare it to the square root of 22 squared. So that's going to be 11 plus 13 compared to 22. Now I know that this is going to be greater than that. So here, the bigger side squared is less than the other two sides. And so when the bigger side, I always compare to the bigger side is less, that's going to be acute. Okay, it's an acute triangle. And make sure you have both those steps in your work depending on how they ask for that. Okay, now here what we want to do is get a common denominator. So there's 3 fractions. So the way we do that is you take the largest number and you say, do those numbers both go into the largest number? 4 does, but 3 does not. So then you take the next multiple of this number, which would be 16. Does 4 go into 16? Yes. Does 3 go into 16? No. So then you take the next one. So you tried 16, now you're trying 24. And they all go into 24. So the least common denominator is 24. Now, to get this to 24, I would have to multiply by 6. So I need to multiply that by 6. So that's going to be 18. To get this to 24, I need to multiply by 8. So this is going to be 8. To get this to 24, I need to multiply by 3. So this is going to be 15. Okay? So the smallest side is 8 over 24. Don't reduce that because we're going to add them together. 15 over 24 compared to 18 over 24. So if I add these two together, that's 23 over 24. That's greater than that, so that is a triangle. Okay? Now we need to square the sides. Now the denominators are all the same, so I don't really need to do those. I just can square the numerators. So this is going to be 64, 225, and 18 squared. You can do that on the side, or that's going to be 324. So if I add these two together, that's less than 300. So now the bigger side squared is bigger. So when the bigger side squared is bigger, that's obtuse. Okay. And finally this one down here. So 1.2 plus 1.6 is greater than 2. So that's a triangle. That's fine. And if we square that, that's going to be 1.44. And if we square this, that's 2.56. And if we square that, that's 4. And that equals, so that's a right triangle. Okay, if you have any trouble with these, you can come to office hours also. That'd be a good idea. Okay, so we've talked about this a few times, and what we want to do here is a couple things. So first of all, as soon as you see this triangle, you want the hypotenuse. So you see the right triangle with an altitude, and that creates 3 similar right triangles. So immediately you should be thinking proportions. We have some proportions here. Another thing you should be thinking is, I want this total side right here. Is there any way I can get that total side? Okay. So in the meantime, I see an A, a B, and a C. So I'm thinking that I'm going to have 3 proportions here. So 3 proportions. I guess I can fit it here probably. Okay. So the first thing is, can I figure out this whole thing? And I can, because this is a Pythagorean triple. So hopefully you're thinking about what I mean there. This is 5, 12, and this is 13. Okay, so the total is 13. That's just one we're supposed to have memorized. You're supposed to memorize 3, 4, 5, and 5, 12, 13 because they happen a lot on tests. Okay, so now I'm going to focus on A here. So if I'm trying to find A is the piece of the hypotenuse that's closest to this leg. So remember, the 3 parts that go up like this, those are all geometric means. So we could actually do that first if we wanted to. So that's a 5. So 5 is the geometric mean. And if we want to move over here to B, B is going to be with this 12. And remember, these 3 are the geometric means. So this is going to be 12 and 12. And finally, the altitude is the geometric mean between the pieces of the hypotenuse, so that's going to be C and C. So all 3 of those segments that go up from the ground are going to be the geometric means. Alright, so let's go back, and these 2 follow the same pattern, the legs. The leg is the geometric mean between the piece closest to it and the whole thing. So the piece closest to it is A, the whole thing is 13. Okay, so multiply both sides by 5. We don't need to cross multiply. We're just trying to get a by itself. So that's going to be 25 over 13, and that's it. We move over here to this side. You could pause it right now, I hope, if you haven't done this already, and think about that same relationship that we had with the red. The leg, this thing that goes up, is the geometric mean between the piece closest to it and the whole thing. Okay, so multiply both sides by 12, and you're going to get 144 over 13. And finally, the altitude. The altitude is the geometric mean between the pieces of the hypotenuse. So this is a little bit awkward, but we just found A was 25 over 13, and we just found that B was 144 over 13. Now, I've tried to go over some little strategies and stuff. So if we cross multiply here, we're going to get c squared, and we're going to get 25 times 144 over 13 times 13. Now, that should be nice. You should be like, okay, that's not that bad, because those are all perfect squares. So the square root of 25 is 5, the square root of 144 is 12, and the square root of 13 times 13 is 13. Nothing reduces there, so that's going to be 60 over 13. Okay, moving right along. Overall, these are kind of long, but you should be fast forwarding through them. Now, vectors. Vectors are easy, but kids get them wrong a lot. So I just think they don't spend enough time because they think it's so easy they never study it again. They forget what's going on here. So graph the vector v with the initial and terminal points. Okay, so the initial, remember your initials are the beginning letters of your name, so the initial point is the beginning point. So that's 1, 2, so that's up here. And then it says the terminal point is negative 2, negative, whoa, just kidding, negative 2, negative 1 would actually be down here. So the vector should have an arrow on it. A vector, remember, has magnitude and direction. The bad guy from Despicable Me. Vector, the orange jumpsuit shark under his living room. Okay. So it says write V in component form. So component form is when you break it down into X and Y. So here's your X and here's your Y. Well, what's happening? It's going 3 to the left and 3 down. So in vector form, we did like greater than or less than, so greater than symbol here. So it goes 3 left and 3 down. So X and Y, same as coordinates. Okay? Then it asks for the magnitude. And now this is a different vector. It's asking for the magnitude of 4, 8. So the magnitude is when you take the square root of the two parts, the sum of the two parts squared. It's basically the Pythagorean theorem. You do an a squared plus b squared equals c squared. But you've already taken the square root of both sides. So that's going to be 16 plus 64. It's going to be 80. And 80 is 16 times 5. So that's going to be 4 root 5. Okay, then it says give the direction of the vector negative 3, positive 3. It's kind of similar to this vector, except it's going 3 to the left and 3 up. Negative 3, positive 3. So I'm just drawing it up here so I can get a look at it. So negative 3, positive 3. So that's pretty straightforward. Remember the direction, so that is never eat soggy waffles. So that's north and then west. And so then you could put the inverse tangent, because we're talking about this angle, opposite over adjacent. That's 3 over negative 3, which would be negative 1. And then that's west. And then this should technically have degrees here, because when we do the inverse trig function, we get it degrees. Now, some of you may have noticed that that's 45 degrees. It's a right isosceles triangle. So you also could put 45 degrees right here if you wanted to. Now, one of the easiest questions on the test that some students get wrong, it's a little bit frustrating, is that you're supposed to know that sum means add. And when you add vectors, you just add the x parts and you add the y parts. So we have 4, negative 2 plus negative 3, negative 8. And we just add those together. So that's going to be 1. And we add those together, that's going to be negative 10. And that's it. So please make sure you get that right. Okay. Special right triangles. So to go from the long leg to the short leg, you got to memorize this. You got to practice it until you memorize it. You divide by radical 3. So that's 9 divided by root 3. We have to rationalize that. So that's going to be 9 root 3 over 3, and then you notice this nicely reduces. So that's going to be 3 root 3. Then when you go to the hypotenuse, you double it, times 2. So this times 2, we have 3 radical 3's. We double that, we have 6 radical 3's. Okay. Here we divide by 2. So to get from the hypotenuse to that, we do the opposite. So here we multiply by 2, here we're going to divide by 2. So if you divide that by 2, it's going to be 3 radical 6. So that's B. Make sure you notice where B is right here. That's a little awkward. So 3 radical 6 is down here. Now to go from the short leg to the long leg, you multiply by root 3. Here we divided by root 3. To go backwards, you multiply by root 3. So that's going to be root 3 times root 6. That's going to be 3 root 18. And that is root 9 times root 2. And root 9 is 3. 3 times 3. Remember, this is times, not adding. So 3 times 3 is 9. So it's going to be 9 root 2. Alright. To go from, I guess I should have focused on A first. It's the same, though, because it's a right isosceles triangle. This 45 should immediately tell you those are both equal, and this is also 45. So 14 divided by, to go this way, you divide by radical 2. To go that way, you multiply by radical 2. So that's going to be 14 root 2 over 2, so that's 7 root 2. And it's isosceles, so they're both 7 root 2. Now, this is one of the easiest things ever on a test in honors geometry at Arborview High School. 45 isosceles, that's going to be root 6. Now to go this way, you multiply by root 2, so that's going to be root 12. Now if this is fast, just pause it or come to office, come to class, stay in class after or come to office hours. Because some people are bored with this, so I'm just trying to go a little bit fast. Okay, find the circumference. So the circumference formula is 2 pi r. Some people say pi d because 2r is equal to d, but I like r because the area formula also has r in it. Okay, so 2 pi times 11 centimeters is 22 pi centimeters. Circumference is like perimeter, just the distance around, so that's it. On the Alex, I imagine, I don't know if they have you multiply that by 3.14, if they have a pi symbol on the side or what, but just do it however the directions say, excuse me. So here we could do pi d, but like I said, I like to use r because that's, so if we divide this by 2, that would be 8 centimeters. It's kind of silly because, well, you'll see why. So 2 pi r, well, when I multiply 2 times r, that's how I got r, as I divided it by 2, so it's just pi d. But just centimeters, not squared, it's not area. Now, so for both of these, so first of all, that's centimeters, so I would put centimeters on there. Now, what you're looking at here really is, think about what the circumference would be, and think about what fraction of the circle you have. So this is 60 over 360. All the way around a circle is 360. And this is 60. So 60 over 360, that reduces to 1/6. So we have 1/6 of the total circumference. So we also need to know the circumference. So that's 2 pi, r is 5. So that's 10 pi. So if we reduce that fraction, that's going to be 5 pi over 3. So 5 pi over 3 centimeters. Okay, and here, kind of the same thing, so it's centimeters, so we'll put centimeters. This is 90, so 90 over 360 is 1/4. Okay, and the circumference is 2 pi r, so that's going to be 12 pi, and 12 over 4 is 3. So that's going to just be 3 pi. And that's it for the review. So that was kind of long, but hopefully you fast forwarded through the stuff you already knew. Have a good day. It's about that time.